Okay, so the goal of this video is to look at L'Hopital's rule. And if you remember, I think earlier this semester, I gave a review question about L'Hopital's rule, thinking we already taught it, and we didn't. Yeah, so here it is for officially L'Hopital's rule, and it's after a French mathematician, L'Hopital, hence the accent and the circumflex above the O. But it helps us evaluate limits when you have an indeterminate form. And remember, an indeterminate form, at least one of the most important indeterminate forms we've had, is 0 over 0. So, like the 0 over 0 sort of masks what's really happening. And we have to maybe dive a little bit deeper to figure out what's the behavior of the function. Well, earlier this year, that involved factoring or knowing some trig identities. But right now, it's going to involve looking at limits and comparing their rates or comparing them as ratios. So really, this is like, we'll need this for the next section, but right now, L'Hopital's rule is just a rule that's based in derivatives. So this could easily have been done first semester. So if you are trying to evaluate a function, and it could be represented as a quotient, and its limit value is 0 over 0. As long as it's not an oscillating function, so watch out for death by oscillation, then the limit of that ratio or that function here is equal to the comparison of their derivatives. And notice it's not the quotient rule, you're just comparing their rates. And the idea here is really to see whose rate is faster, right? And that way that'll help you determine the behavior of the function. So when I look at the first one, like x squared minus 4 over x minus 2, limit as x approaches 2. So, I mean, like if you legitimately try to put 2 into this and you get 2 squared is 4 and 4 minus 4 is 0, 2 minus 2 is 0, so you get 0 over 0. So you get the characteristic 0 over 0. Now last year, we then would have factored the top to make it x minus 2 and then x plus 2. All over x minus 2, we would have noticed that the x minus 2's would have canceled. So we could then have applied the limit to the remaining portion, limit x approaches 2 of x plus 2, which we know would be 4. So that's like first semester way to solve that. Now, second semester way, if you know that you get 0 over 0, then what I want you to do is take the derivative of each of them, but you have to somehow show me that you're doing L'Hopital's rule. So I want you to say it's equal. I want you to put like an H up here for by L'Hopital's rule, the derivative of the top. So the limit as x approaches 2. So the derivative of the top, which is 2x, divided by the derivative of the bottom, which is 1. So like you have to tell me you've done the derivative using L'Hopital's rule. And then you still haven't taken the limit yet, so you still need that. So we don't get lazy on that part. And then as x approaches 2, I can directly substitute that in. That's a 4-to-1 ratio, which we said is 4, which you already knew. Okay, so and that, I mean, that's great. I mean, like same thing we could do here. Like we learned through the squeeze theorem, we proved that this would be 2/3, and we just sort of like memorized it. But if you know that as you approach 0, you still get 0 over 0, that indeterminate form, right? That you could say, okay, by L'Hopital's rule, so it equals by L'Hopital's rule, the limit as x approaches 0 of, now compare the derivatives. The top is 2 cosine of 2x, and the bottom is 3. So now when I let x be 0, cosine of 0 is 1, 1 times 2 is 2, and then the 3 remains the same, so 2/3. So, and L'Hopital's rule can be used over and over and over again as long as you still have 0 over 0. And so, like if I notice this one, if I try to put in 0, I do definitely get 0 over 0. So I could say, oh, by L'Hopital's rule, it's equal to the limit as x approaches 0. Well, then the top function's derivative would be 6x squared plus 24x cubed, and the bottoms would be 15x to the 4th minus 27x squared. And then try again. Well, it's going to be 0 over 0 once more. So by L'Hopital's rule, we can say it's going to be equivalent to the ratio of their limits, their derivatives of the, so excuse me. So the top becomes 12x plus 72x squared over 60x cubed minus 54x. And again, it's still going to be 0 over 0. So by L'Hopital's rule, we do one more derivative. So limit as x approaches 0. So the numerator now becomes 12 plus 144x. And then divided by 180x squared minus 54. So finally, when I put in 0, I get negative 12 over 54, both divisible by 6. So it looks like it's negative 2/9. Now, that might not be the most efficient way to solve this limit. If I, excuse me, factored x cubed out of the numerator to start with, and when I got 2 plus 6, x, and then if I would have factored x cubed in the denominator and got, let's see, 3x squared minus 9, I could have gotten that answer much quicker. So L'Hopital's rule isn't always the most efficient, but sometimes it's very useful when you have a function that you can't easily be factored. And we're going to see in, I don't know if we'll get to in this video or the next video, there are other types of indeterminate forms of numbers, such as infinity over infinity, infinity times 0, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. But the only time you can use L'Hopital's rule to compare those rates is if you have a quotient. So if you're presented any of these other formats like this, you have to somehow convert them to a quotient or to a ratio. So 0 over 0 as is works great. Infinity over infinity, you can use L'Hopital's rule, great. But the other ones, you have to do a little bit of algebra or manipulation. And I mean, like, I always think about like 1 to the infinity, right? Like you're telling me that you take 1 to itself, like 1 times itself, an infinite number of times. That's not equal to 1, right? But it doesn't have to. And this idea of infinity minus infinity, right? There's different levels or degrees or densities of infinity, and so infinity minus infinity may not necessarily be 0. And then, like 0 times infinity, I always like that one too. It reminds me of Harry Potter a bit. I know I have lots of Harry Potter references, but it reminds me when Voldemort and Harry's wands connect for the first time in the Goblet of Fire. And you kind of see that the wands are connecting, and it's like for a while Voldemort's power seems greater, and then Harry's power is greater, and eventually the light of the energy of the wand gets back to Voldemort, and and basically Harry can escape. Spoiler alert. But that's what that reminds me of. Like which one has the greater power, the 0 or the infinity? So anyway, a nice tangent there. So let's maybe do like 1 or 2 examples in this video to show like how we can use L'Hopital's rule even when we don't have the direct 0 over 0 or infinity over infinity. So the first one here, if I try to put x, x going to infinity, so you get e to the negative infinity. So you get e raised to a very, very, very large negative number. So that becomes a 0. And then the square root of infinity still is infinity. So here we go, right? 0 times infinity, who wins? So I can't use L'Hopital's rule yet, but I hope you realize that negative exponent could be rewritten as e to the x in the denominator, right? So now I've created a ratio. So now as you go to infinity, the top is infinity and the bottom is infinity. So that is a ratio. I can now apply L'Hopital's rule. So now that equals, by L'Hopital's rule, the limit as x approaches infinity. Well, remember, it's the ratio of the top derivative and the bottom derivative. So the top derivative is 1 over 2 root x. And then the bottom derivative is still e to the x. Now, I would probably simplify that before I apply the limit. Limit as x goes to infinity. I could rewrite this as 2 root x and then e to the x still down there in the denominator. So now let x go to infinity. So 2 root x times e to the infinity like that's going to get very large very, very quickly, and all under that 1, which means that our overall value is getting smaller and smaller, and it basically approaches 0. So that was nice. So in that case, I guess the 0, 1. All right, now let's see. Well, let's come back to example 5 for a second. Let's go to, I guess we'll just go to 6. Let's go to 6, and then we'll take a break from this video and go to the next video. So as I try to approach 0 here, again, putting in 0 directly, we get 0, because the sign of 0 is 0, minus 0 over 0. So it definitely is 0 over 0. So I'm going to say, okay, well, that's going to equal, by L'Hopital's rule, the limit as x approaches 0. Derivative of sine of 3x is 3 cosine of 3x. And then we get minus 2x minus 3. So that's the top derivative. The bottom derivative is 8x. So again, try to approach 0. Now, cosine of 0 is 1. 1 times 3 is 3, but 3 minus 3 is 0, and there's another 0, and oh, look at that, there's another 0. So we're still of the indeterminate form, 0 over 0. So we could say it's going to be equivalent to comparing the rates as of their derivatives. So limit as x approaches 0. Let's see, now the new derivative would be negative 9 sine of 3x minus 2 all over 8. And now when I approach 0, looks like an infinity, my bad. Now when I approach 0, I get 0 minus 2. So I get negative 2 over 8. So I get negative 1/4. Now, in hindsight, I sort of see a negative 1/4 being like kind of like the lead powers here. But what you have to be careful of is that really only works when you're approaching infinity to see like what takes over, right? So that doesn't guarantee that ratio is going to hold true each and every time. So I definitely caution you of that. Be careful. But because those are the lasting, our highest values, their coefficients should line up so that would be what its limit value is. Okay, so I'm going to go ahead and do the other examples in the second part of the video because each of them take a little bit longer. And I wanted to use this video to kind of give some background to where L'Hopital's rule comes from in terms of comparing those rates, and then what kinds of numbers, what kinds of indeterminate forms of numbers can L'Hopital's rule be used for.